So I have shared with you the notes in Moodle Cloud. You can go through these notes, and also I've given questions that you can try to answer. So we did up to here, Jacobian. Okay. Properties of Jacobian. This is what we completed. Now, so next topic is maxima and minima. This is for function of two variables. So maxima and minima for function just a second. So maxima and minima for okay. Now a function f of x comma y is said to have a maximum at this point x comma y equal to a comma b if f of a plus h comma b plus k is greater than 0, oh sorry, less than f of a comma b, f of a plus h comma b plus k is less than f of a comma b for all h comma k approaching 0. That means in the neighborhood of, that is in the neighborhood of a comma b, the point a comma b, f of a comma b is the largest value. So this is the definition of a maximum at a comma b. So for minimum, similarly, a function f of x comma y is said to have a minimum at x comma y equal to a comma b if f of a plus h comma b plus k is greater than f of a comma b for all h comma k tending to 0. Now this can h comma k can be positive, h comma k can be negative. So, but they are small values of h and k. That is in the neighborhood of a comma b, f of a comma b is the smallest value. So now note some important points to note. I will show some figures to you. Let us. So look at this. There's a function. It's a 3D function. So I'm just orienting. So now if I see parallel to, this is the XZ plane that I'm watching. No, it is in a reverse direction. No, it's minus. Yeah, this is plus. Okay, now I'm witnessing XZ plane. That means from Y, from the direction of Y I'm watching. So this is a 3D surface. This curve is, this is the curve. Z is under root of 9 minus x square minus y square. So here we see that the curve increases, reaches at x equal to 0, it reaches the maximum value 3, and again it decreases. So now this is an isometric view. Now this is a plane z equal to 3. Now z equal to 3 touches, it touches the um, top surface. Okay, it touches the top surface. So this particular point is the point of maximum. So here you can see that. Yeah. So the curve reaches the top and then recedes and it touches this particular plane. So this particular point is called as the stationary point. And this is a plane, which is, this plane is tangential to this curve at this point. So this is the point of maximum. So at 0, 0, there is in the neighborhood of 0, 0, all values are less than function value at 0, 0, which is 3. So there's an example. I'll take a snip. Okay. Next, the same expression. Now I will do another way. I will take z is equal to minus. So this is the curve now. And let us change the state, the plane. Z equal to minus. So now this curve at this point, yeah. So this plane now z equal to -3 touches this curve at 0, 0 at x comma y equal to 0, 0. And so value of z at that point is -3. Okay. So, and this is the point of minimum. In the neighborhood of 0, at 0, the maximum value is minimum value is -3, and values in, in the neighborhood of 0 is greater than -3. So this is the point of minimum. Okay. This is the point of minimum. Just a second. So this is the point of maximum, point of minimum. Now, we should be careful that sometimes you get something called as the saddle point. Saddle point, let us check this. So here is an example of a stationary point, a point where, you know, the point, the function attains maximum. This is a point where function attains minimum, but this is what is called as a saddle point. Now, saddle point, you look at this. Look at this particular surface. Now, from if you go along this curve, this dot red point is a maximum along this curve. So this is a point of maximum for this curve along this particular line that I'm showing here. But then you take this path, this line, this red dot or red point is the point of minimum. So depends on which curve that you are choosing along the surface. This point is either a point of maximum or a point of minimum. So from the surface point of view, this is neither a point of minimum nor point of maximum. So this type of equation, this is actually a portion of the graph of z is equal to x square minus y square. It is hyperbolic paraboloid. This is hyperbolic paraboloid. Okay. So this is an example. So for this curve, here, this example of point of maximum. This is an example of point of minimum. Now, here, this 0, 0, x, y equal to 0, 0 is a stationary point. This is called as a stationary point. It is point where you get the tangential plane, horizontal tangential plane. Okay. Now here, again here, x, y equal to 0, 0 is a stationary point. Okay. This plane z is equal to 3 is the tangential plane or the tangent plane. And here z equal to -3 is the tangent plane. Now here, this point here, this red point here, this point is neither a point of maximum nor point of minimum for the surface. Okay. However, if I draw along this curve, the point is maximum along this curve. Right. And okay. The point is the point of minimum along this curve. So from the point of view of a surface, it is neither a point of minimum or point of maximum. Such a point, derivative will be 0 for that at that point. Okay, we will see that the derivative will be 0. both derivative with respect to x and derivative with respect to y will be 0. Such a point is called as the saddle point. Okay. So in one direction, it will be maximum, and another direction, it will be minimum. Uh, so now let us, this is our understanding, geometrical understanding of maximum, minimum. Now, how do we, from calculus point of view, verify the conditions for maximum and minimum? Just like in functions of a single variable, we had uh, that first derivative is 0 and the second derivative is negative at that point, then that point is the point of maximum. And if first derivative is 0 and the second derivative is positive, then that particular point is the point of minimum. So that was done in functions of a single variable. So now we will evaluate, we will try to find out how to evaluate for two variables. Conditions for f of x comma y to be uh, to be maximum or minimum at some point a comma b. So for that, so let delta be f of a plus h comma b plus k minus f of a comma b. So clearly, when delta is negative in the neighborhood of a comma b, then f of a comma b is the maximum value. Correct? Because all points in the neighborhood are lesser than f of a comma b. So f of a comma b will be the maximum value. So if delta is negative. Uh, Clearly, again, when delta is greater than 0 in the neighborhood of a comma b, then f of a comma b is the minimum value. Correct? So in the neighborhood, all values are greater than f of a comma b. So f of a comma b will be the least of all the values. So these two. Now, how to find this difference? So we use Taylor's theorem for two variables. What it says is, now Taylor's theorem, we know for f of a plus h how to do Taylor series expansion. So now it is a plus h and b plus k. The Taylor series expansion is, first f of a comma b, f of a comma b plus h times dou f by dou x plus k times dou f by dou y at a comma b. After doing this derivative, substitute a and b. Now plus 1 by 2 factorial h square dou square f by dou x square plus 2hk dou square f by dou x dou y plus k square dou square f by dou y square at a comma b plus so on. We just need these three terms sufficient. Why? The first term is required because we want to find delta. So from here, we get delta is equal to f of a plus h comma b plus k minus f of a comma b. This will be equal to h times dou f by dou x plus k times dou f by dou y okay at a comma b plus 1 by 2 factorial h square dou square f by dou x square plus 2 hk yeah 2 hk dou square f by dou x dou y plus k square dou square f by dou y square a comma b plus the third order terms. Now h and k are very, very small. They are in the neighborhood. Uh, um, this point is in the neighborhood of a comma b, means h and k are very small. They can be positive numbers or negative numbers, but they're very, very small, close to zero. So they're fractions close to zero. So the dominant terms will be the least powers. Higher the powers, the value of h cube, h power 4, k cube, k power 4 will be much, much smaller than this. So that will all go to zero pretty much very fast. So dominant terms are these. So delta will be determined by these values. The first two terms pretty much. Now, um, now for maximum or minimum, for maximum delta has to be negative. For minimum delta has to be positive. Now let us say uh, you take in one direction h, you keep h constant. That means h you are not changing, but k you are changing. And at some point, dou f by dou x will be equal to 0. Let us say this term vanishes. And dou f by dou y doesn't become 0. Now, k can take positive values and negative values. So delta will keep changing from negative to positive as k is varying. So which means for all points in the neighborhood, for all points in the neighborhood, this uh, delta value is not negative or not positive. So I've given one example that move along a line where h is constant and let's say df by dx is 0. Now the value of k will determine the sign of delta, but we want the sign of delta independent of h and k. Okay, independent of h and k, because in the neighborhood here, the figures that we draw, h and k can be positive or negative, but independent of h and k, this delta has to be negative or positive or throughout the neighborhood, but it doesn't happen so. So what we can observe is that for delta to be, okay, for delta less than 0 or for delta greater than 0, in the neighborhood of, in the neighborhood of a comma b, that is for a plus h comma b plus k, where h and k take small positive or negative values. Okay. Now for this to happen in the neighborhood of, so this is a bracket statement, neighborhood I've explained here. So for delta to be less than 0 throughout in the neighborhood, or for delta greater than 0 throughout in the neighborhood, uh, the only possibility for this to happen only when h dou f by dou x plus k dou f by dou y at a comma b is equal to 0. Now this is independent of h and k, right? H takes the value, whatever. This should be 0. Either h and k can take for any value of h and k. For any value of h and k, this should be 0, which implies dou f by dou x at a comma b should be 0, and dou f by dou y at a comma b should be 0. So this is understandable. Along the direction of x, the derivative must be 0, and along the direction of y, the derivative must be 0. So here in this particular example, it's not, it's hung, just a second. Yeah. Yeah. So let us explore. So green line is x-axis. Now red line is x-axis, green is y-axis, and blue is z-axis. So now you see here, along the x-axis. So red line is the x-axis. So along the x-axis, that means along this particular line in the xz plane, okay, I can show that curve also. XZ plane means y equal to 0. So y equal to 0 is a plane. And now let us do the intersection. Uh-huh. H and F intersection path. Okay. I am showing the intersection path. So the intersection path of H and F, that means the curve and the XY plane is this. Okay. This is the intersection part. So along this curve is changing along x is changing along this curve, and z is changing, y is constant. So what we get is dou z by dou x, or dou f by dou x, is equal to 0 at this point. Okay, that is the intersection path. I'm removing this plane. Now this plane is of course a stationary plane. We can, yeah, this forms the tangent at this point. So derivative is 0. Now let us do another intersection path of, x equal to 0. X equal to 0. It's not an equation. All right, I'll just change this. This makes it easier. I will change this. Instead of y equal to 0, I put x equal to 0. That's it. Now they see the intersection path has changed. Okay. Now this path, red line is the x-axis. No. Yeah. Now this is the y-axis. So I'm moving in the y direction. And now in the y direction, the derivative so dou f by dou y is 0. So if I show this, this is 0. So for along both the lines, so intersection 1 and intersection 2, I will okay. There's the intersection path of P and F. Okay. So now I'm just showing two intersection paths. One, two, the two intersection paths. Yeah, in the plane. So for the curve, you are able to see here in the direction of F, in the direction of X, or in the direction of Y. So red line is the x-axis. Along the x direction, at this point, there is the derivative is 0. And so this is along x, the derivative is 0. And along y, the derivative is 0 again. You get horizontal tangent, this one, throughout. So it's a surface, horizontal tangential surface. So hope you understand what is in two different directions, in x direction and y direction. This has to be 0 independent of h and k, whether um, h is small or k is small. This, if it's 0, this will take care that this is 0. Otherwise, if this doesn't become 0, you neither get the point of minimum nor maximum. So once this is 0, now what happens is the this this is called as the necessary condition. Now a comma b becomes a stationary point, but now the sign is dependent on the second term. So let us examine that. The above is called as the necessary condition for existence of maxima or minima. So a comma b is called as a stationary point. Okay. Now let's determine the sign. So now delta will be equal to 1 by 2 factorial times h square dou square f by dou x plus 2 hk dou square f by dou x dou y plus k square dou square f by dou y square. Now at AB, the sign of this will be the dominant. Just this other all terms will be much smaller than this term. So this uh, is the dominating term. This is the dominating term to determine the sign of delta. Okay. Other terms can be ignored. So let us do this. Now mm, let R be equal to dou square f by dou x square at a comma b, which we can write as fxx at a comma b. Similarly, mm, let s be dou square f by dou x dou y at a comma b, f subscript xy a comma b, dou square f by dou y square a comma b, f y at a comma b. So this is RST. So therefore delta can be written as delta is 1 by 2 factorial h square times r plus 2hk times s plus k square times t, k square times t. Now what we can do, um, we can multiply and divide by r or t, doesn't matter. So one of them. So when we multiply and divide by r, we get this. Now, now what we can do, this is 1 by 2r times. Now we can convert this to hr plus ks the whole square minus um, k square s square plus k square times rt. So 1 by 2r times hr plus ks the whole square plus k square times rt minus s square. So delta is written like this. Therefore, sine of delta is equal to sine of this term 1 by 2r hr plus ks the whole square. H and k are small variable values um, of argument, and r s are derivatives. So remember that rt minus s square. So now here we get, now delta will be positive if rt minus s square is greater than 0. All the terms are positive. This whole entire term will be positive. Then sign will depend on only r. Now if rt minus s square is greater than 0, then delta is less than 0 if r is less than 0. That is f of a comma b is maximum. Or delta is greater than 0 if r is greater than 0. That is f of a comma b is minimum. Correct. So the entire thing, if rt minus s square is positive, then delta delta will be the sign of delta is the same as the sign of r. If r is negative, delta will be negative, which means f of delta is this. So delta is negative means f of a comma b is maximum. Delta is positive means f of a comma b is minimum. So this is mathematically, this is what we will do. Now, if RT minus S square is less than 0, if this is less than 0, this is negative. Now, depends on the value of, now at a comma b, at a comma b, R, S, and T values are fixed, and this is negative. Now, depends on H and K. The combination of H and K, sometimes this term may be greater than this term, or sometimes this term may be lesser than this term. So irrespective of the values of R, the sign of delta will keep fluctuating. So if RT minus S square is less than 0, then delta will change sign. Delta will change sign depending on the values of H and K. Thus, already we know the first derivatives are 0. That is what we found here. We impose the condition, the first derivatives is 0 in along x and y. However, in the neighborhood, the function value is either exceeding or is below f of a comma b. So it is a saddle point. Thus, a comma b is a saddle point. If RT minus S square is equal to 0, then further investigation is required. It is like the second derivative test has failed. Okay. The same thing we can accomplish. Instead of R, we can use T also. Same thing we can accomplish if RT minus S square. So now let us look at, so we can summarize this as the working rule. So working rule to find maxima and minima. Working rule to find maxima and minima. So Z is equal to f of x comma y. So first step, find the stationary points. A comma B. All stationary points where the first derivative along x is 0 and the first partial derivative along y is also equal to 0. The partial derivatives with respect to x and y are 0 at a comma b. So this is a stationary point. Now calculate r is equal to dou square f by dou x square at a comma b, s dou square f by dou x dou y at a comma b, and t dou square f by dou y square at a comma b. So the third step, the second derivatives we evaluate. Now, so first point, if rt minus s square is greater than 0 and r is greater than 0, or r is less than 0, first case, maximum case, then that means delta is negative. So f of a comma b is the maximum value. If rt minus s square is greater than 0 and r greater than 0, then f of a comma b is the minimum value. So point of minimum will be a comma b. And if rt minus s square is negative, then f of a comma b does not have an extreme value. This point a comma b is a saddle point. A comma b is a stationary point, but it is a saddle point because along different paths you get a comma b as the point of maximum and point of minimum along different paths. So it's a saddle point. It's like a point of inflection where derivative is 0, but it is neither a point of minimum nor point of maximum in functions of single variable. So saddle point is like a point of inflection. So next, if rt minus s square is equal to 0, then nothing can be said conclusively. Nothing can be said conclusively. It as it needs further investigation. That means we can check the first derivative test at a comma b along any path, irrespective, along any path, if we can do and show that it is uh, point of minimum or point of maximum along any point or any path, then we can conclude. So this is the working rule. So all the theory we have done, if you can just understand it and just remember the working rule, that is sufficient. This working rule we need to remember. First, find points where first derivative is 0. Next, what you do is find the second derivatives, r, s, and t, and then rt minus s square greater than 0 and the sign of r. Rt minus s square greater than 0 and the sign of r. For if rt minus s square is less than 0, it's a saddle point. So let's do problems. So find the extreme values of z is equal to x power 4 plus y power 4 minus 2x square plus 4xy minus 2y square. So find the extreme values of this. This is a function in X and Y. So first step is to find the stationary points. So dou F by dou X, 4x cube minus 4x plus 4y equal to 0. That is equation 1. So then dou F by dou Y or dou Z by dou Y, 4y cube plus 4x minus 4y equal to 0. So these are the two. Now we have to find x and y such that both are possible. So clearly one point is 0, 0. 0, 0 is 1 point. Now let us subtract. By adding, we get, okay, let us do this. By adding 1 and 2, we get 4 times x cube plus y cube equal to 0, which implies x plus y into x square minus xy plus y square equal to 0, which is x equal to minus y. This term can never be 0 for real values, but x equal to minus y. So if we substituting, we get, substituting this in 1 and 2, either 1 or 2. So let us substitute in 1, 4x cube minus 4x minus 4x equal to 0. So 4x cube minus 8x equal to 0. So x cube minus 2x equal to 0. So we get x into x square minus 2 equal to 0. So we get x equal to 0, x equal to plus root 2, and x equal to minus root 2. Now if we subtract, so we got 3 points. Now let us subtract and see. By subtracting, 1 and 2, so 1 minus 2. So 4 times x cube minus y cube, then minus 8x plus 8y equal to 0. So we get 4 times x cube minus y cube minus 8 times x minus y equal to 0. So 4 cancels twice, then we have x minus y times x square plus xy plus y square minus twice of x minus y equal to 0. So we get x minus y times minus 2 equal to 0. And This can never be 0. Uh, so the only possibility we get is x equal to y, and x equal to y if we substitute in any of these equations. So 4x, 4y cancels. Then we get 4x cube equal to 0. This gives that x equal to 0, y equal to 0. So here in the previous case, when x equal to 0, this implies y is minus x 0. Here y will be minus root 2, and here y will be plus root 2. So the three stationary points, the stationary points are 0, 0, first one, root 2, minus root 2, and the third one is minus root 2, root 2. This is the third one. Okay. So at these stationary points, we have to find RST. So let us find the second derivative. So this is the first derivative. Second derivative, let's do. Differentiating twice, we get 12x square minus 4. Okay. And d square f by dou square f by dou x dou y will be differentiating with respect to y. We get 4. No, we get 0. No. This with respect to x, yeah, we get 4. We get 4. And then dou square f by dou y square, we get 12y square minus 4. Now, let us consider the first point. The first stationary point, 0, 0. Now, at this point, what will be R? Now, R is this fxx at 0, 0. So this one, substitute 0, 0 in this expression 3, 4, 5. So in 3, when you substitute 0, 0, we get minus 4. S is constant irrespective of x and y. It is 4. T, the second derivative with respect to y at 0, 0, we get minus 4. Now we get RT minus S square is minus 4 into minus 4 minus 4 square. 16 minus 16 equal to 0. So nothing can be said. So further, so RT minus S square is 0. No conclusive result. So further investigation is required. Now, how to do further investigation? So along different paths, we have to check. Say, so let us investigate because it is 0, 0. So let us investigate along x-axis. And so what is x-axis? Y equal to 0. And y-axis, how the derivatives vary. So along the x-axis, what happens? So along x-axis, so put y equal to 0. So f of x comma 0, how will it be? The equation. Go up all the terms. So y is 0. So 1, 2, 3 terms become 0. So you have x power 4 minus 2x square. The curve will be x power 4 minus 2x square. Now, this is x square into x square minus 2, which is x square into x plus root 2 and x minus root 2. Now, f of 0, comma 0 is equal to 0. All right. And in the neighborhood of 0, and when x lies minus root 2 to 0, union 0 to root 2. So x lies in between root. So f of x comma 0 will be negative. It's a negative value because in between, one term will be positive, other will be negative. Okay. One term is positive, other term is negative. So it is negative in the neighborhood of 0. Now let us along y-axis, we'll see. So put x equal to 0. So f of 0 comma y. Okay, f of 0 comma y. Let us see. X 1, 2, 3 times 0, exactly the same. So we get y power 4 minus 2y square, which is y square into y square minus 2, which is y square into y plus root 2 into y minus root 2. So f of 0 comma 0 is 0, and when y lies between minus root 2 and root 2, so y takes this value, then f of 0 comma y is negative. That means 0 comma 0 is a maximum value. Now let us choose any path. So along, say, y equal to x, y equal to mx, we can take, but y equal to x. So we get z is f of x comma x. So substitute in the given equation. So when you get non-conclusive result, this is what we need to do. So now z f of x comma x, which is x power 4 plus x power 4 minus 2x square plus 4x square minus 2x square. These cancels, you get 2x power 4. Okay. Now, in the neighborhood of 0, now z is 2x power 4 is always positive. 0 comma 0. So here 0 comma 0 along this path is the point of minimum. Okay, I'll draw here. 0 comma 0 is a point of minimum along the path y equal to x. Okay. However, it is point of maximum along y-axis and x-axis. So point of maximum along x-axis, it's a point of maximum. Along y-axis, it's a point of maximum. But along an inclined path, y equal to x, we trace the curve and we find that the curve is having a point of minimum. So therefore, along different paths, 0 comma 0 is different. So 0 comma 0 is a saddle point. So neither a point of minimum nor point of maximum. Okay. So let's look at the second stationary point. So stationary point root 2 minus root 2. Now R is fxx 12x square minus 4. S fxy is plus 4 and t fyy is 12y square minus 4. So when we substitute these values, 12 into root 2 square minus 4. So 12 to is 24 minus 4 is 20. This is 4 and this is also 20. So RT minus S square. RT minus S square is greater than 0. 20 into 20 minus 4 square. It is greater than 0. So now sine of delta is same as the sine of R, which is R is greater than 0, which implies if R is greater than 0, that's a point of minimum, because delta is f of a plus h comma b plus k minus f of ab. So if it's positive, in the neighborhood values are greater and the value of ab is the least. So therefore root 2 comma minus root 2 is the point of minimum. Right? For third stationary point also, it is minus root 2 plus root 2. See the signs, because it is 12x square minus 4, 12y square minus 4. That minus sign doesn't change. You get exactly the same thing. So minus root 2 on root 2 is also the point of minimum. Okay. Again, RT minus S square is 400 minus 16 greater than 0. And R is greater than 0 in this case, so is a point of minimum. So both are the points of minimum. So minimum value we can find out. So Z is equal to f of root 2 minus root 2. So Z is here. Z is here. F of root 2 minus root 2. So root 2 power 4 is 2 square, that is 4. Now root 2 minus root 2 power 4 is 4. This is minus 2 into 2. Then plus 4 into root 2 into minus root 2. And minus 2 into 2. So 4 plus 4, 8, minus 4 minus 4, 0. And then 4 root 2 minus root 2 becomes minus 8. So answer is minus 8. So again, z f of minus root 2 comma root 2, again the same. 4 plus 4 minus 2 into 2 plus 4 into minus root 2 times root 2 minus 2 into 2 minus 8. The points of minimum are plus root 2 minus root 2 and minus root 2 root 2, and the minimum value at both these points and both the points. Okay, so this is how we do the problem of maximum and minimum. So I'll give you a gate problem to solve. Before I do a gate problem, yeah, I can give a gate problem. That's not a, then do the applications. 2010 gate problem. This is given a function f of x comma y is equal to 4x square plus 6y square minus 8x minus 4y plus 8. The optimal value of f of x comma y is a minimum equal to 10 by 3, a maximum equal to 10 by 3, a minimum equal to 8 by 3, a maximum equal to 8 by 3. Okay, one of the, okay. So now this is z equal to f of x comma y is 4x square plus 6y square minus 8x minus 4y plus 8. So first step is dou f by dou x is 8x minus 8 equal to 0, which gives x equal to 1. If x equal to 1, okay, and simultaneously dou f by dou y is also should be equal to 0. So 12y minus 4 equal to 0. So we get y equal to 1 by 3. Therefore, there is one stationary point. Therefore, stationary point because both have to be simultaneously 0. This is what the case is. Now, f(xx), the second derivative with respect to x is 8. So it is constant. So this can be taken as r. Now, f(xy) is 0. So s is 0. And fyy is equal to 12. Therefore, RT minus S square is 96 greater than 0, and R is equal to 8, which is greater than 0. Therefore, delta is greater than 0. This means it's the point of minimum. This means the point 1, 1 by 3 is the point of minimum. And the minimum value is substitute f of 1, 1 by 3, 4x square plus 6y square. So 4 into 1 square plus 6 into 1 by 3 the whole square minus 8x minus 4y plus 8. So minus 8 into 1 minus 4 into 1 by 3 plus 8. So we get 4 plus 6 upon 9. That is 2 upon 3. Minus 8 minus 4 upon 3 plus 8. So plus 8 minus 8 cancels. So we are left with 4 minus 2 by 3, which is 10 by 3. So the correct answer is, it is the point of minimum. And the minimum value is 10 by 3. So the minimum equal to 10 by 3. This is the correct answer. Okay, so this was a problem on gate, which was very simple. It was not complicated. It was not a saddle point. It was a simple equation. And we were able to solve it very, very easily. Let's do another problem of gate, previous gate question. The distance between the origin and the point nearest to it on the surface z square is equal to 1 plus xy is options A 1, B under root 3 by 2, C under root 3, and D 2. So what is to be minimized? the distance, the distance between origin to any point on this surface, that has to be minimized. So let S be the distance of any point x, y, z from origin. So S square is x minus 0 the whole square plus y minus 0 the whole square plus z minus 0 the whole square. Now, if x comma y comma z lies on the surface, z square is equal to 1 plus xy, then what happens? S square is x square plus y square plus 1 plus xy. So we want to minimize this function. So let f of x comma y be equal to this. And we want to find the minimum value of this function. We need to find minimum value of the above function. If this is minimum, then s square will be minimum, which means s will be minimum. Okay, this is how we need to do. So let us minimize that now. Dou f by dou x is 2x plus y, and dou f by dou y is 2y plus x. Now both should be equal to 0. One point very clearly is 0 comma 0. Solving, we get these are two lines, y equal to minus 2x and y equal to minus x by 2. They both have only one point of intersection. We get x equal to 0 and y equal to 0. So the stationary point is 0 comma 0. Now fxx is 2, which is r. Fyy is 2, which is t. Fxy is 1, which is s. So in respect of 0 comma 0. Now rt minus s square is 2 into 2 minus 1, which is 3 greater than 0, and r is greater than 0. Therefore 0 comma 0 is the point of minimum. The minimum value is f of 0 comma 0. Substitute 0 comma 0, we get the value 1. Therefore the distance, minimum distance is 1. S square is 1, minimum value. So the distance is 1. This is the answer. So in GATE, we get values, functions like this, functions of multiple variables, maxima and minima problems. Of course, compared to functions of several variables, The problems of maxima and minima on functions of single variables are more in GATE. So, but still, suppose we get one problem sometime, uh, we should be able to do it. We should not fumble. So that's the idea. One more example for today, and we can stop. This time, let us this is a good one. A rectangular box open at top is to have a volume of 32 cubic feet. Find the dimensions of the box requiring least material for its construction. So when we say least material for construction, so material, it is like thin sheets, either metallic sheet, whatever it is, the material. So surface area times thickness gives the volume of the material. So material has to be least, means the surface area has to be least. So there's a box which is open at top. So there's a rectangular box. So let's say we fix the X, Y, and Z axis here. So now this length is X, this length is Y, and this length is Z. Now volume given, what is the given condition? Given is that X into Y into Z is 32 cubic feet. Now surface area, see this all is closed on all sides except on top. So front, back, right side, left side, and bottom all are closed except on top. Now surface area, we'll denote as S, is X into Z. So this portion, front and back, so twice, plus. Next, Y and Z, right and left. So Y times Z twice. But then bottom is only X into Y, but not at top. So XY. So this is the surface area which has to be minimized. So this function has to be minimized. Okay. So we'll treat this as function of. Now, what we have to do, there's a function of 3 variables. We have to convert it to function of 2 variables. So S is f of x comma y, which is xy, plus 2x plus y into z is 32 upon xy. So we get xy plus 64 times x plus y upon xy. So the function which was of 3 variables, we have converted it to the function of 2 variables. So let's do. So now fx dou f by dou x is y minus 64 by x square equal to 0. Next, fy is equal to dou f by dou y, which is x minus 64 by y square is equal to 0. Now we need to solve these two. So solving, so take y, substitute y is equal to 64 by x square from 1 into for solving. So you get x minus 64 by y square 64 square by x power 4 equal to 0. So x minus x power 4 by 64 is equal to 0. So 64x minus x power 4 equal to 0. So 64 minus x cube times x equal to 0, which means either x equal to 0 or x equal to 4. 4 cube is 64. So, and now, so substitute. If x equal to 0, y does not exist. So 0 comma 0 cannot, that 0 term, when x equal to 0, y does not exist. When x equal to 4, then y will also be 4. So when x equal to 0, y is not defined. When x equal to 4, y is equal to 64 by x square, which is equal to 4. Therefore, 4 comma 4 is the stationary point. So 4 comma 4 is the stationary point. And now let us do this. F second derivative fxx is the derivative of the first derivative, which is y minus 64 upon x square, which is minus 128 upon x cube. F xy is d by dy of y minus 64 by x square, which is 1. And fyy dou y of x minus 64 by y square, just minus 128 upon y cube. So now f r is fxx at the stationary point, minus 128 by 64, which is minus 2. S is 1 and t minus 128 by 4 cube, which is minus 2. Therefore, RT minus S square is 3 greater than 0. But R equal to minus 2 less than 0, which implies delta will also be less than 0, which implies oh, I'm sorry, I made a mistake. This will be plus minus 2 by x cube. So this will be plus, this will be plus, this will be plus, this will be plus. That's what I was getting at. So R is greater than 0, delta is greater than 0. So if delta is greater than 0, it means f of 4 comma 4 is the minimum value. Okay, so now x, y, z is equal to 32. So when x equal to 4 and y equal to 4, z is 32 by x and y. Just to, therefore, the optimal dimensions of the box for least material is x equal to 4, y equal to 4, and z equal to 2. These are very practical engineering problems. So, and now people are using, data science, machine learning problems. There are multiple variables and you have to minimize certain parameters, minimize or maximize certain parameters. That's where, differential calculus, whatever you are learning here is used. If you go through some data science course or machine learning course, one part of it is, optimization and linear regressions. So in that, these concepts, what we are learning here will be used. Okay. And of course, this is a very practical engineering problem for most engineering streams. We will have to minimize use of material, or we have to minimize a certain parameter, which is dependent on multiple other parameters. So this was the class on maxima and minima today. I'll stop here. So please practice.